This Week in Virology, the podcast about viruses, the kind that make you sick.
Hello, ASV. It's time for This Week in Virology. This is episode 395. Today is June 20th, 2016. This episode is brought to you by CuriosityStream, a subscription streaming service that offers over 1,400 documentaries and nonfiction series from the world's best filmmakers. Get unlimited access starting at just $2.99 a month. And for our audience, the first 2 months are completely free if you sign up at curiositystream.com/microbe and use the promo code MICROBE. Hi, everybody. I'm Vincent Racaniello, and you are listening to the podcast all about viruses. Today, we're coming to you from Blacksburg, Virginia. We are on the campus of Virginia Tech. We are here for the annual meeting of the American Society for Virology, and this is a return visit for me. I was here a couple of years ago. That was TWiV 285, Hokies Go Viral. I spoke with XJ Meng and Sarah McDonald about their work. Today, joining me for this episode from southeastern Michigan, Kathy Spindler.
Hi, everybody.
From north central Florida, Rich Condit.
Hello, everybody.
And our guest was the keynote speaker at this meeting the other day. He is from the Mayo Clinic in Rochester, Minnesota, Stephen Russell.
Hi, everybody.
Welcome to TWiV. And by the way, you can take pictures. Okay, they said this morning you can't take pictures at data talks, but we're talking here, so you can't take pictures of the data, right? So take all the pictures you want. You can ask questions. We have a mic up here if you are brave enough to come up here. You can get recorded. Anything else? I think that's all.
Weather report.
Weather report. How it looks great.
It's great. It's 77 degrees Fahrenheit, 25 degrees Celsius. Bright, sunny day.
And what's the dew point?
That's Rich's responsibility.
It's okay.
I'll get it for you.
So Stephen, we're going to talk a bit about your science, but I want to first know a little bit about your history, where you're from, where you were educated, and so forth.
So,
Oh, by the way, before you start, sorry, I twisted his arm to get him here today. And I twisted it a little too hard, I'm sorry. What is that? What's that about?
this is actually seriously embarrassing. 1 week ago yesterday, I was out cycling, and I was very close to my house going downhill. I had something I was holding in my right hand, and my bike was accelerating, so I pulled the front brake with my left hand. And I don't remember anything for the next half hour, but apparently I staggered into the house, bleeding from my head, barking orders at my family. And I was taken to the emergency room and spent 8.5 hours there. I spent the next 3 days sleeping every 2 hours. And then the day after that, I went into the clinic to visit with a patient who had multiple myeloma, who I'd been seeing for some time. And this patient said when I walked into the room, "What, you've been biking again?" And his wife said, "Were you wearing a helmet?" And I looked pretty sheepish and said, "No, I wasn't wearing a helmet." And she said, "Because you love the wind in your hair." And I said, "Did I actually say that to you?" She said, "Yep, 2 years ago when you fell off your bike, that's what you did." So please, everybody here, get a bike helmet. I now have one.
All right, now you can tell us about you.
Oh, about me, right. So yeah, I was born and raised in England on the south coast, went to boarding school in Scotland, went to medical school in Edinburgh, University, and then moved down from Edinburgh to London, where I completed my medical training at University College Hospital and at the Royal Marsden Hospital. I actually did my PhD while in London at the Marsden, at the Chester Beatty Labs with Robin Weiss and Mary Collins. And then I moved to Cambridge for 7 years. And from where I worked in the LMB, initially Centre for Protein Engineering, under Greg Winter and Alan Furst. And I was a consultant hematologist there as well. And then I moved after 7 years in Cambridge to Mayo Clinic. That was now 18 years ago, to build what is now a pretty big oncolytic virotherapy program at the Mayo Clinic.
So you specifically went to Mayo to do an oncolytic virotherapy program?
Yeah, it was the opportunity of a lifetime, because Mayo Clinic had decided around that time that they needed to get into gene therapy. And they had spent a couple of years trying to recruit, 3 years actually, trying to recruit to that program. And they just had most recently been trying to recruit Malcolm Brenner, who had negotiated with them for about 9 months, got this wonderful program into shape, and then decided to take a job at Baylor College of Medicine. So Mayo asked him for names, and he fortunately gave them my name as one of the names on the list. So they came to me from Mayo with a sort of ready-made opportunity, 10,000 square feet of floor space, a plan for a manufacturing facility to make virus, a plan for a toxicology group, 7 faculty positions to fill. I mean, it truly was the opportunity of a lifetime, and I was very fortunate.
But the way you describe it, they were thinking gene therapy, because 20 years ago, what was the status of viral oncotherapy?
Yeah, at that time they were thinking gene therapy, and but they were quite happy that it would be oncolytic virotherapy as the main focus, provided that in addition we recruited in people to cover other aspects of gene therapy.
But had you any virus experience? Did you do that in Robin Weiss's lab?
Yeah, so I decided at medical school that I was going to do oncolytic virotherapy. I actually had, I had a sister who was 27 years old when I was 21, and I had a phone call one morning at medical school to say she died in a house fire. And that was just after I'd completed my microbiology finals. And I'd done pretty well, and I'd been invited back for a distinction oral. So I was reading about viruses as I traveled home to her funeral. And it kind of occurred to me then that viruses were an untapped bioresource that could be used for cancer therapy. And so I decided, okay, that's what I'm going to do.
But at that time, had anyone yet used a virus for oncotherapy?
They had, and many people had. I just simply wasn't aware of it. But
Okay.
I mean, it's obvious once you think of it. It's worthwhile to try.
So can you give us a brief history, to paraphrase Stephen Hawking, a brief history of viral oncotherapy? When did it actually start? Who were the first to do it?
It started, I mean, there are anecdotal reports of cancers regressing after what may have been a viral illness, very early 1900s. But it was really in the 1950s that Chester Southern, who was working at Cornell in New York, decided to move ahead and start administering viruses to people with cancer. And he worked closely with a woman, Alice Moore, who was doing a lot of lab work with mouse models in conjunction with him.
This is the same Chester Southern that injected people with HeLa cells, right?
Yeah, for which he got into serious trouble.
Right.
Yeah, Chester, he was a very enthusiastic scientist. He was confounded by the fact that the responses to virotherapy with these unmodified wild-type viruses were quite variable. And he wanted to try and learn more about the process, so implanted tumor cells in the forearms of patients with cancer, and in fact of prisoners who didn't have cancer, who were apparently happy to participate in these studies. He didn't actually tell people that he was injecting tumor cells because he was concerned about frightening them. And he did have 1 or 2 cases where the tumor cells actually metastasized from the site of implantation. And I mean, it was a different era, and I think we can all look at it now and say, well, clearly that was bad. We've all been sort of disciplined to think that way, and I think around that time it was a very different perspective.
In my remembrance, and this could be wrong, the reovirus was the first to really get this field going, right? The idea that a reovirus could be specific for RAS-positive cells, is that right, or were there others?
Well, there was the Onyx 015,
okay.
The adenovirus that supposedly targeted P53 deficient cells. Yeah, reovirus was one of the early ones too. But I think, Bob Martusa actually was ahead of that with his TK-deleted herpes virus, which he used to treat U87 gliomas in nude mice. And he really, I think he got the field going again. Because if you go back over that history, it's very difficult to know exactly why the field fizzled back in the sort of 60s and 70s. I think in part it was because chemotherapy was coming through and people really thought that they had the answer for cancer. It was also because you couldn't easily manufacture viruses, you couldn't engineer them, you couldn't purify them, and so they weren't really druggable. And so people didn't know how to control them or make them into drugs. So, and then there was Chester getting into trouble. But there were quite a few people doing it. There were other studies at the time, and there was a Japanese group led by Dr. Asada who used mumps virus for cancer therapy, and they reported on over 200 patients treated with many responses. But they were using saliva and blood and body fluids containing the virus as the therapeutic. It was really a different era.
What cancers were they treating?
A whole variety of different cancers. And they were typically very advanced cancers. And often there was reports of tumors undergoing central necrosis and sloughing. But typically they grew back fairly rapidly post-therapy.
So as of today, roughly how many different clinical trials are ongoing for viral oncotherapy?
I don't actually know the number. I would, at a guess, I would say 50.
Yeah. So 50.
Yeah.
And are these are with only certain numbers of viruses have been used and developed for these? Roughly how many different viruses?
Well, I think in the clinic there are anything from 12 to 15 different viruses. And then preclinically, there are quite a few more coming through. But within each virus family, within some of the virus families, there are a number of different viral constructs that are being evaluated. Herpes virus has been pretty popular, and I think there are probably 4 or 5 herpes viruses in clinical testing.
So, do you think at one point all cancers will be treated with viral therapy, or will it depend on the cancer and the vector and so forth?
Yeah, I think, I'm a complete groupie for oncolytic virotherapy. So as far as I'm concerned, yes, all cancers are potentially amenable to oncolytic virotherapy. I think, there's a huge amount of ground that needs to be covered before that happens. And, I don't want to give people the wrong impression and think that it's going to be next year or 5 years from now that everything has changed. I think it'll take much longer than that. But, when you look at what viruses can do in nature, I mean, fundamentally, they destroy tissue, and they do so with a high degree of specificity. Typically, they do it incompletely. Typically, there's a huge amount of variability between individuals who are infected with a given virus. And we understand many of the reasons for that, to do with innate and adaptive immunity and virulence factors and interaction with the whole sort of genetic makeup of an individual host is going to influence virus infection. So I think that's all stuff that we have to work on, of understanding exactly how much virus we give, what route we give it, how frequently we give it, in order to achieve that total tumor destruction that we're looking for.
So how does one go from a virus to treating people? What does someone look at the properties of a virus and think it might be amenable? How does the whole process work? Give us an idea.
Well, I think it's most of the viruses that are currently being tested in the clinic have been developed not through somebody saying, okay, I'm going to look at the whole spectrum of viruses out there and pick the best one. It's been individuals who work on a given virus saying, right, I'm going to see if I can turn this virus into a therapeutic. So that's an important caveat. The issues that have to be addressed in order to justify taking a virus into the clinic, the first one is specificity. And it's probably selectivity is a better word, because most of the viruses currently being tested are not specific, but they have selectivity built in at different levels. And if you have enough levels of selectivity, you can become specific. But if you do have a specific virus, you can pump up the dose and you can make it more virulent, and you can thereby potentially achieve greater tumor destruction. So specificity is really a key parameter at the baseline. And the stability of that specific virus, because otherwise you have the concern that you're going to somehow be unleashing a new virus on the human population. If you've done something to increase the ability of the virus to destroy the tumor, and then it learns how to escape from the tumor and infect other tissues, then you'll run into a problem. So you've always got this balance between specificity and stability of the virus that you have to consider in your design phase. And I think generally what people have done up till now is just go with attenuation, because that gets you around this problem of stability and specificity. We know a lot about a lot of vaccine strains and how stable they've been over many years, and how they've not reverted to wild type, and they're not going to revert to wild type. And it turns out that for many of those attenuated viruses, tumors are particularly susceptible to them by virtue of defects in the tumor that result in a weakened defense against the virus, either defects in the innate immune defenses or defects in the ability to be recognized by the adaptive immune response.
For the benefit of folks out there in TWiV land who didn't get to hear your talk, I'd like to hear you go over just a bit more about mechanism, because so far you've talked mostly about the viruses as killing the tumor cells, but in your talk you talked about immune mechanisms that come into play. Could you address that a little bit?
Yeah, okay. So there are broadly two major ways in which a virus can destroy a tumor. One is that it comes in, it kills a few tumor cells, provokes a local inflammatory response, and thereby enhances, and there's cross-priming of the immune system against the tumor antigens. And so it's a way of boosting, it's an in situ vaccine to boost anti-tumor immunity. And then the other major mechanism is that the virus actually spreads through the tumor and behaves as a more of a pathogenic virus and destroys tumor cells. And then at the end of that, there's a recruitment of the immune. So you're either going predominantly after the anti-cancer immune response and trying to boost that, or you're trying to bring to bear this other aspect of viruses. Most of what has been seen and achieved in the clinic up till now has been the first of those two. And the approved herpes virus, TWiV, or Imlygic, which Amgen is now selling, that's a herpes virus with, it's got a gamma 34.5 deletion, ICP47 deletion, to attenuate it somewhat and make it more cancer specific. It's got the GM-CSF gene in it because that enhances the uptake and cross-presentation of tumor antigens by antigen-presenting cells in the tumor when the tumor cells die. And that virus has shown activity in melanoma in boosting the anti-tumor immune response. So it's administered repeatedly into a cutaneous melanoma lesion. And what you see is the other lesions in the skin regressing in those patients who respond. But the virus does not spread from the injected tumor to other tumors. And it doesn't seem to matter either whether the patient's previously been exposed to herpes or not, at least according to the analysis of the data currently available.
So that's consistent with the notion that you're stimulating an immune response that's having a collateral effect.
Yeah.
Okay.
Yeah.
So since you mentioned the TWiV, this has been approved by the FDA for melanoma, correct? Now, is it only indicated when other treatments have failed, or could it be used outright?
It could be used outright. I think it's been approved, though, for melanoma that has failed frontline therapy. And typically with anti-cancer drugs, that's the initial approval is going to be for advanced disease, and then additional trials are done to bring it up front. Certainly what Amgen are doing is they're capitalizing on, because this whole immuno-oncology approach to cancer therapy has really taken off in recent years. And these checkpoint inhibitor antibodies are now being fairly widely used in a variety of different malignancies that appear to be responsive to immunotherapy. Melanoma was the first of those, and so what Amgen are doing is combining their virus TWiV with ipilimumab, pembrolizumab, with anti-checkpoint inhibitor antibodies. And they've already completed a 200-patient trial comparing TWiV with TWiV plus IPI in patients with advanced melanoma. Don't know what the result of that is, but their early phase 1 data in that combination were pretty good. And there's now a 600-patient trial randomized ongoing with the combination of TWiV plus pembrolizumab.
Can you tell us how these antibodies work?
Yeah, so the whole immuno-oncology field is, I think, based upon the fact that tumors acquire mutations. Cancer is a genetic disease, effectively. And if you look at the genomes of tumors, you'll find that there are lots of mutations in those tumors, some of which are occurring in the coding sequences of proteins that are expressed in the tumor. So these non-synonymous mutations result in the expression of peptides that have the potential to be immunogenic. Some of those expressed peptides are actually going to be immunogenic, and they'll be displayed in the patient's MHC in such a way that T cells can react against. So tumors that have a high mutational burden have probably more of these immunogenic peptides than tumors that don't. So they're intrinsically immunogenic. So how do they actually persist and exist in the patient? They do so by a couple of different mechanisms, but one of the major mechanisms is that they express on their surface one of these molecules that can put the T cells to sleep, basically. So it's PD-L1 interacts with PD-1 on the surface of the T cell and stops the T cell from doing anything when it arrives in the tumor. So then if you give an anti-PD-L1 or an anti-PD-1 antibody, you block that interaction, and now the T cells can actually do their thing and kill the tumor. So that's that's the whole basis of the checkpoint inhibitor antibody therapy. But there's got to be some T cells reactive against the tumor for that to really be effective. And so in conjunction with those PD-L1 antibodies, it's how do you actually boost the number of T cells recognizing tumor antigens. And that's where this kind of in situ vaccination approach with oncolytic viruses is really quite appealing. Because it's agnostic, it's not a vaccine against NY, ESO, or, the E6, E7 antigens of human papillomavirus. It's just, it's something that allows the immune system to recognize what's already there on the tumor cells.
Right. So I have to make a plug for fundamental research, right? Because PD-1, PD-L1 were just discovered that way, and now they're used translationally. Isn't that great? It means we have to continue both.
Absolutely, absolutely.
So I got a request from someone to learn a little more about the vectors. This is a vector group. These are virologists mostly. And you work a lot with measles, treating myelomas, right? Could you tell us about that vector, how it's designed, and what everything is used for?
Yeah, so it's pretty simple with the measles. We haven't done anything super clever. A lot of it is just serendipity. That when the virus was isolated from David Edmondson's throat, it was grown on cultured cells and moved around between different cultured cells. And one of the things the virus learned to do in adapting to grow on cells was to use CD46 as a receptor. And as luck would have it, most human tumors express pretty high levels of CD46. I mean, it is ubiquitously expressed on human cells, but tumors have approximately 10-fold higher density. And so tumor cells, if you have an index-infected tumor cell, it will fuse with neighboring cells. Whereas if you infect a normal cell with the Edmonds lineage measles, it won't fuse with its neighbors because the density of CD46 is lower. So, that's a kind of fortuitous thing. The other thing is the virus has lost some of its immune combat proteins. The V and C proteins are actually not completely non-functional, but they've lost some of their functions. And so, again, we then have tumor specificity because the cell lines on which the virus was adapted to grow, as well as the tumors, have defects in their innate immune defenses.
So in your talk, you described using the measles vector for treating myeloma, and you described using a VSV vector for treating hepatocellular carcinoma. We've talked a little bit here about selectivity and vector choices and stuff. How did you arrive at that choice of using measles for the myeloma and VSV for the hepatocellular carcinoma? Or is this serendipity as well? What's the thinking?
Okay, so just back to that.
He's got a little grin on his face.
Just back to that engineering question, though. We in addition, we inserted a transgene into that measles virus, coding for NIS, the sodium iodide importer, and that is the molecule that concentrates iodine in the thyroid gland in order to make thyroxine. You can use radioiodine to treat metastatic thyroid cancer. And so with that NIS gene, we can actually do imaging to monitor where the virus goes in the body. We can also give I-131 to boost the efficacy of the virus. So it's sort of a gene that we desperately wanted to have a reporter gene in the virus, because how else do you know what's happening in vivo? But in addition, we wanted that reporter gene to be justifiable on some other basis. Right. And so it's kind of neat for that reason. With the choice of measles for myeloma was on the basis that measles is a naturally lymphotropic virus. And so we thought that was a good way to go. Multiple myeloma patients have seriously impaired immunity because it's a disease of antibody-producing B cells, and they have, as part and parcel of the disease process, they have a hypogammaglobulinemia. So they have low antibody titers, and then we treat them with all these drugs that kill B cells. And so that makes their immunity even worse. So we wanted to be totally safe. And that was another reason for going with measles. We thought, okay, we've got a problem with the immune defenses already being up. But on the other hand, if we can actually make this virus work, then it's totally population safe because of all the history of measles vaccination. Mm-hmm. So and the myeloma population was good because of this lowered immunity, so we might be able to get in with the virus in some of the patients and actually reach the tumor and damage it. With VSV, we've sort of thrown that thinking out of the window. And we've said, okay, the immune system is actually a significant barrier to efficacy. Prior exposure to the virus is a problem. So what virus can we use where there is a low prevalence of immunity? And VSV is a logical one. You know, many groups have worked on VSV for many years. We didn't discover its oncolytic activity. That had been sort of, John Bell up in Canada and Doug Lyles and Glenn Barber. Many groups had been working on VSV as an oncolytic. And we just thought, okay, well, let's focus our machine on the VSV, because we at Mayo had all the manufacturing, the tox capability, the experience with doing clinical trial with measles virus. And so we could now bring another virus into that machine, and that was the one we chose for those reasons. On the safety front, we thought, well, it's a pathogen of cattle. It causes a blistering, non-fatal disease in cattle of mouths and hooves, and humans get exposed frequently, and if they work with those cattle, but there haven't been deaths of infected humans. So we had that sort of safety aspect to it as well.
Can I interject? Kathy, when you were in Holland's lab, didn't people get finger infections with VSV?
So I did work in Holland's lab with VSV, and Bert and I just exchanged glances about that. I think I was one of the graduate students who didn't get VSV, but there were others that I heard about.
And when you did get VSV, how did it present?
I think it's your typical flu-like symptoms, right, Bert? Yes.
It's quite often asymptomatic. I think one or two people in my lab may be VSV seropositive, so they may not benefit from what they're working on if they get cancer. So we need to develop some other viruses too.
So has measles been used for other cancers as well?
Yes, we have a number of trials ongoing at Mayo Clinic in different malignancies. Actually, I think the first trial that was done with measles was using the off-the-shelf vaccine, and it was a Swiss group that used this. I can't remember exactly who it was, to inject cutaneous T-cell lymphomas with a very small dose of measles vaccine, and they reported they had a paper in Blood quite a long time ago that said, yes, we think we're seeing some efficacy. And that was at a very low intratumoral dose. I think the maximum was about 10 to the 5th.
So I wanted to ask you to tell for the audience that wasn't there at your keynote, or the audience at home, how your student met the Edmonston, the namesake of the virus.
Oh, this was a high school student working in my lab, actually. A very bright, very ambitious high school student who was going in for the regional science fair. And he initially worked on HIV vectors. He was trying to construct HIV vectors that would be good for efficient transduction of mouse cells, and he took that to the science fair, and it didn't do very well. So, well, it did pretty well in my view, but he didn't get to the international science fair, which was the next level. So he came back and he said, I want to do something more exciting. I'd like to display a peptide on the surface of measles virus. So I said, you can't possibly do that, you're a school kid. But anyway, he persisted, and we got some people working with him to help him do it. And he displayed it was an MSH peptide he displayed on the virus. And he was able to demonstrate that that peptide was displayed on the surface of the measles virus as a C-terminal extension of the H protein. And he went and presented it at the regional science fair, got to the international science fair, came to DC, and he was standing at his poster there. He actually won Best Biology prize. He got
Nice.
$20,000 towards his college tuition. And had breakfast with the president too afterwards. So, but this David Edmondson showed up at his poster and said, "Do you know where that virus came from?" Came from my throat back in 1954. So that's where I got that photograph from.
Nice.
So I wanted to ask you about a couple of modifications that are made to viruses to improve their oncolytic abilities. Maybe you could just tell us a little bit about these. First, for VSV, you're changing the glycoproteins. Maybe you could tell us what that does. And then microRNA addition and drug convertases. Could you just give us an overview of what they're doing?
Well, the whole point of going after the surface glycoproteins is to try and redirect virus entry. And actually, you know, we displayed on a lot of different viral glycoproteins, one of which is VSV, but we cannot redirect the entry of VSV. The problem with VSV is that we haven't been able to identify mutations that ablate the natural tropism of the virus, and it's an extremely broad tropism. And it's reported to be through LDL receptor, but LDL receptor is a protein. I think there's more to the story than we currently have there. We displayed on retroviruses, a way back when, and we found that we could redirect the attachment of retroviruses, but that didn't lead to entry. And then with Roberto Cattaneo at Mayo Clinic, we've had this long-standing collaboration of working on the H protein of measles. And there, if you display on the C-terminus of measles H, and you ablate the binding sites for CD46, SLAM, and now Nectin-4, that virus behaves beautifully. You can actually redirect the tropism of measles anywhere with displayed antibodies or other protein binding domains on the surface. So that's that targeting method. Another targeting method is microRNA targeting, and there we found this is particularly effective with picornaviruses. It also works with measles, but not with VSV, where you build into the virus a target sequence recognized by a microRNA in a cell that you don't want to damage. So we started out with a picornavirus that we could give to mice. It would destroy the myeloma xenografts in the mice, and then it would kill the mice. Coxsackie virus A21 would kill the mice with myositis. So we then engineered into that virus a muscle-specific microRNA target. So now it infects muscle, the virus genome is destroyed, but it still infects the tumor and is able to kill tumor. So that microRNA targeting it's just taking out specific tropisms rather than building in new tropisms. And what was the third?
The drug convertases.
The drug activating enzymes, I think they're not so much a targeting methodology. I think, the idea there is you have your virus deliver something that's innocuous. Because, we all want to increase the potency of these oncolytic viruses, but we know if we put in a toxic gene, then we're potentially creating a new pathogen. And so if we put in drug convertases, then we can just deliver something innocuous, and then when it's in the right place, deliver the drug to mediate that targeting. It's similar with the Nis protein, actually, and delivering the radioiodine after you actually know that the virus is safely at its destination.
I have to say that you're getting to me. I've been a skeptic for a long time, but you made the comment in your presentation that really right now we're driving a Model T Ford, okay? And we're just learning this. And this sort of conversation about the modifications that can be made and the targeting and all of the potential in our burgeoning understanding of the mechanism actually is compelling. You got me, okay? I'm getting the feeling that there might be hope for me down the road.
Well, that's great. So now you have to start working on oncolytic viruses.
Actually, we didn't, for the listeners out there, we didn't talk about the success of the measles virus against the myeloma. You did a trial with a number of patients, one of whom is apparently cured, right? And I wanted to, you can talk about that, but I just want to take a moment to remind the listeners that we actually did that paper on TWiV. It's TWiV 298, MVNis de Myelo, one of Alan Dove's best titles. But you might summarize that for the listeners.
Yeah, so that's Stacey Erholz, and she is not cured. She had very advanced myeloma. She had all available therapies at the time, it was 3 years ago, and she'd had 2 autologous stem cell transplants where we harvest stem cells, we give very high dose myeloma to wipe out her marrow, and then we give the stem cells back. She was relapsing fairly rapidly after a second stem cell transplant, out of options, decided to go for the viral therapy and had a complete response. She had a large tumor on her forehead the size of an egg. Her children had called it Evan. She had multiple other tumors on her PET CT scan. Her bone marrow was diffusely infiltrated with myeloma, and it all disappeared. 9 months later, she had a focal relapse. So the tumor on her forehead began to regrow. And knowing myeloma as we know, we fully expected that the systemic relapse was coming. But we decided at her request just to irradiate the tumor on her forehead. So we just gave local therapy, fully expected myeloma to come back, and it didn't. And then 6 months ago, this is now 2.5 years out from therapy, she started to notice a lump on her chest wall. This one she called Chester. And again, Chester was a focal relapse, and there was no evidence for myeloma coming back in the bone marrow or anywhere else. And we irradiated that. She's now 3 years out, and she feels great. She's just the biggest advocate for oncolytic virotherapy. But she may not be cured. You know, it may be that she'll have another relapse. It may be that she'll have a systemic relapse. And, you know, every clinic visit she has is kind of a worry. What are we going to find? You know, we can't tell her, okay, you know, go away, you're cured. But myeloma isn't curable at the moment. You know, we can never say that to anyone.
But the progress of her disease, it sounds as if it's somewhat unusual. Do you associate that with the particular sort of therapy that she's had? Is there something unusual going on here?
Yeah, there is. And that is what we're desperately trying to understand, because, you know, she is what we would like to, we'd like to achieve the same thing for other patients with myeloma and for other patients with other types of cancer. So the key is to understand what's going on. I mean, this is unusual. You know, we've treated other patients with myeloma, we've not achieved the same outcome. And she was antibody negative. She had been vaccinated against measles virus after her stem cell transplant, after her first stem cell transplant. Very often we revaccinate people after they've been through a stem cell transplant because it so significantly knocks down their immunity. So she'd been revaccinated, and then she'd had a second stem cell transplant, which had knocked her measles antibody titer way back down again, but not her T cell response to measles. So she still had anti-measles T cells, which is kind of interesting. You know, is that important? We don't know, but she did have high measles T cells, low measles antibody. And then we just recently have obtained tumor from Chester, which we fully sequenced. And we find that she has a very high mutational burden in that tumor. multiple myeloma typically has approximately 50 non-synonymous mutations per tumor, per patient. She has 530 non-synonymous mutations, which puts her at the very high end of mutational burden and suggests that this is an intrinsically immunogenic tumor that she has. And for that reason, we can postulate that the virus not only caused tumor reduction, but also boosted her anti-tumor immunity. And then when she had that focal relapse, the irradiation served to boost the anti-tumor immunity. And it's well recognized that there's something called the Abscopal effect, when you can irradiate a single lesion and obtain an immune response against a systemic disease.
Could you please wear a helmet?
I was thinking I should probably have worn one to this meeting.
No, that's not what I meant. I meant this is great stuff, and you're an important part of it, and you shouldn't be cracking your head open so you can't do it. Right? I want to take this moment to just mention that all these modifications you're doing to these viruses are gain of function, right? So I want to put out there this, there are many people who are against gain of function work with certain viruses, but you never can restrict it. And if you do restrict some, it will spread to others, but we don't want to limit our ability to change viruses for oncotherapy. I'm sure you're aware of this movement with influenza transmission and so forth, but have you thought of it in the context of your viruses?
Yeah, we worry about it constantly. I mean, it's the potency safety conundrum. And, as I was saying earlier, I think we want specific viruses that are not capable of escaping from the specificity that we endow them with. And then, if we had such a virus, then we can make it as potent as we want. And so there are various different things to consider, one of which is safety switches. If anyone, and that's why I'm sort of, calling people to sort of turn their minds to this and come up with ideas for what can we do. If there was some simple modification we could make to all of our oncolytic viruses that would allow us then to just shut the infection down at whatever time we choose to do so, and that mechanism wouldn't be lost through virus mutation in the patient, that would be really very reassuring. But people drift in the direction of let's put in more virulence determinants, let's put immune combat proteins. Look at what viruses do to actually have their evil way with their host. Let's steal those tricks and put them into our oncolytics, and I'm strongly opposed to that.
Could it be as simple as having antibody therapy ready in case anything happened? We do that for other virus infections.
You need a virus that you can shut down with an antibody, and I think it's rarely that simple.
All right. One last technical question. In terms of delivery, you've talked about your success story with the myeloma. It sounds like that was given intravenously and spread, but you mentioned earlier that most of the time these viruses are given right into the tumor. So can you give us an overview of that?
Yeah, the intravenous versus intratumoral question I think is really very interesting because natural infection is typically more in line with the intratumoral approach. And intravenous is it's a dodgy delivery mechanism because you're delivering quite large nanoparticles. And if you look at the tumor vasculature, some tumors have leaky blood vessels, but they're rarely leaky to the extent that viruses can actually escape through the gaps between endothelial cells. So your intravenously administered virus may never actually see the target if that tumor has intact blood vessels. So by delivering a small amount of virus into the tumor, you're absolutely dead certain that you put the virus in contact with the tumor cells and initiated the infection. And then you can rely on that infection spreading rapidly through the tumor. So that's where you do need a virus that's fast moving, and you do need a decent dose to go in. And you do need to worry about the distribution of the virus within the tumor that you've injected. And you may then be able to rely on bloodstream, sustained viremia is what you're going to get if you get viremia from a local site of infection. The kind of viremia you get from infusing virus is short-lived, rapid decay viremia, and that may not be sufficient as well to get you where you want to go. So I think the intratumoral has a lot going for it, in that you can give a lower virus dose and you can be more certain that you've actually hit your target site. And at least you will then get that immune-mediated anti-tumor activity, even if you don't get the whole oncolytic paradigm.
I wanted to ask one question. At the end of your talk the other night, you said there's a great need for more young, innovative experimental virologists. So in just a very short time, could you describe how someone could properly train for a career in viral oncotherapy?
That's a difficult one. I think, my sort of hope is that people who've trained in fundamental virology, who've really got the discipline, who really understand viruses, who've done that kind of painstaking, curiosity-driven fundamental research, will then turn their attention to the problems confronting us within the oncolytic virotherapy field, and will rigorously develop those kinds of solutions that we're talking about here. How to get the specificity, how to introduce safety switches. These kinds of problems, I think, are going to be far better approached by people who have that virology training. So I think it has to come through the kind of classical virology pathway, and then turn attention to these other sort of more applied aspects. But there has to be a love of engineering. I mean, there really does. I think that because many people do have just that mindset of I want to find out how nature works, and I don't really want to exploit it or change it. I just want to know. But I think there's room for all these sort of people with engineering bent, but they do need to go through the discipline first.
We've actually had a few emails from people wondering how to have a career in oncolytic virotherapy. Do they need to work in a lab that's doing it? But this is the answer for them, right? All right, we have just a couple more things for you. I want to tell you about the sponsors of this episode first, very briefly. Having sponsors allows us to do more, travel more, and do more kinds of podcasts. And our sponsor for this episode is CuriosityStream, which is a subscription streaming service of nonfiction documentaries from the world's best filmmakers. It was founded by John Hendricks of Discovery Communications. It's available on all sorts of platforms like the web, iOS, Amazon, Kindle, and Fire, and so forth. It's available in 196 countries. They have science, technology, nature, history, documentaries. For example, Next World with Michio Kaku. They have a number of movies on viruses. These are all nonfiction. Inside the Human Body, Microbirth, Leaps in Evolution. And I think some of our listeners might be interested in this. And there are monthly and annual plans available, starting at just $2.99 a month, the cost of less than the cost of a cup of coffee, of course. Check out curiositystream.com/microbe. Use the promo code microbe during your sign up, and you'll get unlimited access, completely free for the first 60 days. That's 2 months free of one of the largest 4K libraries around. curiositystream.com/microbe, and use the offer code microbe at sign up. The last thing we do here on TWiV is our pick of the week. Kathy, what do you have for us today?
So I have something that Vincent actually helped in. The ASM has just put out a YouTube video, and it's entitled, "Can You Explain Your Science in 30 Seconds?" And it was just filmed at the ASM meeting where Vincent was just a few days ago, put together by Chris Kondayan and Ray Ortega. And they went around and interviewed a few people to try and explain their science in 30 seconds. And it's just a really great video. And I think in the spirit of the fact that we usually have the communications workshop on Monday, this is something for you to think about. At the end of the video, they invite you to explain your science in 30 seconds, and then upload it to microbeworld.org. So it's just really fun to take a look at. And I have one other communication thing to plug, and that is the career workshop tomorrow afternoon at 4:30. If you've seen really good slide presentations here, or some that maybe weren't quite so good, if you go to this talk by Jean-Luc Demont, he's just a very excellent, entertaining speaker, but all about communication, and he'll tell you some really good ways to improve your slides.
Stephen, can you explain your science in 30 seconds or less to your mother or father?
No, but I want to be like Anne Palmenberg. Awesome. That's the best talk I've ever heard.
So you're not going to do it? You're not going to even try? One of the guys we tried to film, we went up to people in the floor of the meeting. It was a lot of fun. And we would say, can you explain your science in 30 seconds or less? And one guy said, no, I can't do it. Rich, what do you have for us?
All right, I'll see if I can do this in 30 seconds. This is just something I ran across. Apparently, we have another satellite besides the moon, sort of. There's an asteroid out there that's somewhere between 120 and, this was discovered just a few weeks ago. It's about between 120 and 300 feet in diameter. How they figure this out, I don't know. But it orbits the sun, but it's kind of doing the Watusi with the Earth. So it gets ahead of it, and then it falls behind, and it gets ahead of it and behind. So it's under the influence of the Earth's gravity. So in effect, it's orbiting the Earth at the same time. But lots of times, it never comes closer than 9 million miles. Apparently, it's been out there for about 100 years, and they figure it'll be out there for another couple of hundred, and then probably take off. So we're not alone.
I like the way you did the little Watusi. It was good. Very good. My pick is a new book by Siddhartha Mukherjee. Anybody read Emperor of All Maladies? Isn't it great? So he's an awesome writer. He got the Pulitzer Prize for that book, A History of Cancer. He wrote a new one now called The Gene, An Intimate History of the Gene, and just came out a few weeks ago. He's just a great writer, and he traces trying to understand the gene from way back to the present day. And of course, he's got a chapter on modifying our genome as well, of course, to sell the book. But he's a wonderful writer. He tells stories beautifully. I've just started reading it, and it's just great. The Gene, An Intimate History by Siddhartha Mukherjee. I wonder, can you win 2 Pulitzers?
I don't know.
I don't know.
Why not?
Why not?
not?
Could win two Nobel Prizes, right? And we have a listener pick from Dylan, Vincent and friends. I came across this video linked below describing the microsculpture project of Livan Biss. He uses a light microscope together with commercial photography techniques to capture incredibly detailed images of insects. The website for the project contains some of the beautiful images he obtains. I'm jealous of any listeners around Oxford that might be able to attend the exhibition. So he makes these huge images of insects, and they're incredibly detailed, but then you can go on the website and zoom in on and see the individual hairs. Absolutely beautiful stuff.
The video is pretty cool too, because they show making the large prints that are going to be up in this exhibition, and how he does the photography. It's just amazing.
Pretty cool what you could do with tech these days. All right, that's episode 395 of TWiV. You can find it at iTunes at microbe.tv. And we love getting questions and comments. We usually make them part of the episode. And you can send them to TWiV at microbe.tv. And please consider supporting TWiV and all the other science shows at Microbe TV. We have an account at Patreon, patreon.com/microbetv. If half of our listeners gave $1 a month, we'd be able to do a lot of cool things. So think about doing that. If you want to give a chunk of money at once and you don't want to subscribe, you can go to Microbe TV, microbe.tv/contribute. And stay tuned for another Drobo giveaway. Some of you may remember we had a contest a number of years ago. We gave away these storage units for your data. Now Drobo wants to do it again because they had a great effect, and this is going to be a networked storage unit. We're going to give a couple away. We'll have contests, some kind of creative contests, so look out for that. I want to thank everybody who was here today. Our guest, Stephen Russell from the Mayo Clinic. Thank you so much for joining us.
Thank you for having me. I really enjoyed it.
Good. And be careful, please, because you're doing important stuff and you need to keep that up. Kathy Spindler is at the University of Michigan in Ann Arbor.
Thanks, Vincent. This was a lot of fun. Thanks, everybody.
Rich Condit is at the University of Florida in Gainesville, Florida. Thank you.
Thanks, always a good time.
And I'm Vincent Racaniello. You can find me at virology.ws. I want to thank the American Society for Virology for letting us do this year after year, and to the great audience who all came and filled this room. I'm really impressed that you come year after year to hear this. I don't take it for granted at all. I really appreciate it. You've been listening to This Week in Virology. Thanks for joining us. We'll be back next week. Another TWiV is viral.